Okay, so remember what we're in the middle of. We are looking at the the following problem. Right? So the problem is the following. Right? We have some function f of x. Right? We're given some Schwartz function f of x, and we're looking at the upper half plane. Right? The upper half plane. Right? Where is x is y is greater than 0. We want a function u so that agrees with f on the boundary of the upper half plane, and we want it to satisfy. We want it to be a harmonic function on the interior, right? On the interior of the upper half plane, on the upper half plane. The upper half plane we should consider to be an open set. Okay. And then we played the usual game. We took the Fourier transform in the first variable, right? And we saw that u of xy had to be something convolved with something whose Fourier transform was e to the negative 2 pi c y. So that if a solution existed, it had to be something like this. Okay, this was our guess that the Fourier transform is. Okay, and so the thing that we needed to do right now was figure out what function has a Fourier transform that looks like this, and this is the so-called Poisson kernel, right? So we defined to make the definition the Poisson kernel in the upper half plane. And we had a Poisson kernel on the circle. We've got this Poisson kernel on the upper half plane. And you should be thinking, why are they both called the Poisson kernel? And we'll get to that shortly. Poisson kernel in the upper half plane is defined like this. Pyx is 1 over 5 y over x over plus, right? And I think we just about started this lemma saying that Poisson kernel really is the guy whose Fourier transform is this, right? So if you take the thing whose Fourier transform we want, and you hit it with the inverse Fourier transform, then you get this thing that we've just defined. Okay, right. So that says, if you read this, right, it says that the inverse Fourier transform of this thing actually is Poisson kernel, right? If we want to use a different notation, make it more obvious. Okay, and the second fact is just the first fact. It's just the first fact again, that if you take the Poisson kernel and you take its Fourier transform, you get the thing designed. Okay, but once we prove the first fact, we have the second fact, right? We don't need to prove the second fact. It's the same thing. Right? That the Fourier transform of this is that. Well, that's the same thing as saying that the inverse Fourier transform of this is that is this. Okay, so and the proof of this is actually just a calculus problem. Okay, so I don't know if we even want to do it, but I'll sort of sketch it. Divide the integral into 2 parts. Right, the integral from 0 to infinity and the integral from negative infinity to 0. And then you just calculate each part using calculus, and then you put them together and you get that. Okay. So just looking here, we have e to the negative 2 pi absolute value cy, e to the 2 pi cx, right? You write that as e to the 2 pi I x plus iy c, I'm sorry, this should be c. This should be c also, sorry. Okay, because we are taking the inverse Fourier transform, right? So it should be integrating on the frequency side. Okay, and then, well, this is e to the some constant times c, and then you just use calc 2 or 1 or whatever, right? And you get that this is negative 1 over 2 pi I x plus I1, right? And then you do the other guy. The other guy turns out to be 1 over 2 pi I x minus I1, and then you add this together and you get the Poisson kernel. So it's we could have actually this is right. If we were the ones figuring out this theory, we'd say, okay, we want something whose Poisson whose Fourier transform is this. Well, let's take the inverse Fourier transform of this. The inverse Fourier transform, and then we would just calculate it, and we would have ended up with Poisson kernel. Right? That would be a cool way to present it. But I found that those of you who want to be teachers, I found that presenting things in such a manner never works. That is, it's better to lay out what you're going to get first and then explain it, rather than sort of go along, and then say, ta-da, this is what happens. I think that's actually more like how it actually happened, right? But somehow it doesn't work teaching-wise. Because a deductive presentation is far more effective than inductive. Why? Okay. Everyone all right so far? Okay. So we've got the Poisson kernel, and so again, some sort of miracle happens. We are again. We're lucky. Are we lucky? Or does this always happen? Or under what conditions does this happen? We're lucky again to have the following phenomenon occurring. That the Poisson kernel is an approximation identity. The Poisson kernel is a good kernel on R as y goes down to 0. So, and again, sort of the proof, the main part of the proof is the last part. So the main part is to show that the integral from delta, that if you choose any neighborhood of the origin, then eventually the amount on the outside goes to 0. Right? So you take any delta in the origin, eventually most of the mass is concentrated inside that delta neighborhood. Right? That's the property that you need to show. And so you examine this integral. And again you find that you are back in calculus class. And so using elementary calculus, you get something like this. And then, as y goes to 0, then you get the juice inside. So it's So it turns out this thing is an approximation identity. Okay. Okay. So these are not the interesting parts of the material today. There are sort of like two interesting parts. First is the next thing we're going to do, showing that this actually, that convolving with the Poisson kernel actually does give you a solution, and the solution vanishes at infinity. And then the more interesting thing, I think, is the mean value property. So what we'll see is that any harmonic function satisfies what's called a mean value property, and this mean value property will give us uniqueness of the solution. This mean value property is actually really crucial. Okay, if you go on into PDEs and stuff like that, you'll see the mean value property again.
The mean value property guarantees uniqueness.
It's
like in this case? Or
in this case, that's right.
Will it in most cases for like harmonic functions? Will it do that for all harmonic functions?
No, so you have to have some conditions.
Okay.
Yeah, what we'll see is that, so the first thing we'll see is that that our solution has a decay at infinity. Okay. And then what we'll see is that if you have a solution that has the decay at infinity, then it's unique. Okay. And that uniqueness will follow from the mean value property. Okay, but you need to have that decay. You need to have that decay at infinity. Those of you who have seen, who've taken complex analysis before, some things may look familiar to you before we start talking about the harmonic functions. Okay, so first, so let's give the theorem saying that the solution actually is a solution. If F is in Schwartz class, and you take U to be F convolved with P. Okay, you take this guy to be F convolved with P. Okay, this is just wonderful, actually. Okay, you guys should. Then, well, you have a harmonic function, right? So this is a way of creating harmonic functions, right? You take this guy, you convolve with Poisson kernel, you get a harmonic function, okay? And in particular, U is in C2. You see what happens, right? As y goes down to 0, right? We just noted that p sub y is a good kernel, right? So what's going to happen? This guy is going to recover the function, right? It will converge back to the initial data as we wanted it to, right? Right. So u x y goes to f of x in that uniformly because of the Schwartz class decay as y goes to 0. Number 3, u dot y converges to f dot in L2 as y goes to 0. And these look pretty similar to the statements we made before about the heat equation on the line, right? And you can probably guess how things are going to happen, right? This you're going to just differentiate on the integral sign, and it'll work out. Just this thing you're going to use the fact that Poisson kernel is a good kernel, and this thing, what are you going to do here? What did we do in the case of the heat equation on the line? We were trying to get the L2 control of this thing, and we did it by invoking we switched it over to, we used the Fourier transform, right? We took the Fourier transform and said, well, look, the Fourier transform of this difference is going to be the same L2, have the same L2 norm as the original by Charles, right? So you know, everything that happens here is going to be basically identical to what happened before. So the book leaves it as exercises. I'm going to leave them as exercises. The thing that's different is the following. U x y, so U actually vanishes at infinity in the sense that U x y goes to 0 as the absolute value of x plus y goes to infinity. And this will be the thing this will be the quality that we'll use to guarantee uniqueness of a solution. It's actually false. One of your homework problems, I think, is to show that if you don't have the vanishes at infinity condition on, then in fact you have multiple solutions. And this is related to remember when we got the ordinary differential equation, we tossed out some solutions, right? This is where they get back at us, right? Okay. So okay. So this last thing, actually the proof of this last thing is along the lines of the bounds that we did last time to show that that the function was in the Schwartz class uniformly. Okay, so it's the same sort of trick of dividing the integral into two parts. Okay. So proof of form. Proof of form. Okay, so let's get two estimates. Okay, we want to get two estimates on the size of f involved with p1. Okay, so the first one is that we can bound this by some constant times 1 over 1 plus x squared plus y over x squared plus y squared. Okay, and we're going to play the trick that we played last time. Okay. We're going to take the integral, and then we're going to split it up into two parts. A part where t is small, and a part where t is large. So we call this A, and we're going to call this one integral 1, and this one integral 2. Okay, so thinking about 1, in integral 1, just like we saw last time, you know that x minus t is basically the same thing, the same size as x. Right? Because it's the size of this is trapped between 1/2 the size of x and say 2 times the size of x. So it's basically the size of x. And so so using the fact that f is a moderate decrease. In fact, it's better than that, but all we need is that it be a moderate decrease. We say, well, look, f of x minus t then is controlled by some constant over 1 minus x minus t squared. But this thing is basically, you may have to throw in some different constant, but you can control it with c over 1 plus x squared. So that gives us the first part. Right? Okay. And then the second integral, second one, I'm sorry, the second integral here, we use the fact that since t is bigger than x over 2, well, we know that py t, which is y over t squared plus y squared, is bounded by some constant over times c over x squared plus y squared. Right? Because if we replace this thing by something smaller, right? The thing just gets bigger. We may have to put in some constants to deal with the 2. Okay. But this works. Everyone all right with that? Okay. Right. So the end, right? Right. So we know that that the Poisson kernel here is bounded by y over x squared plus y squared, right? So the second integral, right, is controlled by this constant times the integral of f. Right, times the integral of f over the whole line. But that's finite. Right, that's finite. And so, of course, you're noticing that this is the common abuse of notation of analysts. We use c for every constant, even though c may be a different constant. But it's clear, right? This is just another constant. And we can make them the same constant by letting them be the maps of the constants. Okay, so yeah. So that's what we do. I'm not really ashamed. Okay, so is that clear? Do people get this? I think it's pretty simple. Right? And it's basically the same thing we did last time, right? It's exactly the same thing we did last time. We have this place where this thing is basically x, and then the other thing, we control the kernel. Right? We control the size of the kernel, and that's it. So that's estimate 1. Estimate 2 is this one. C over y. Okay. And you notice that that the supremum of pyx over all x in R is controlled by some constant c over y. Because it's y over x squared plus y squared, right? As x ranges, then this thing is basically 1 over y. Okay. So this one I actually didn't prove, but can anyone give me a reason why this is plausible? Why does this make sense? Well, you know that this guy, is controlled by c over y, right? And convolving with f, right? F is a function of moderate decrease, right? So x you want to think of as bounded. It's controlled in the 1 over 1 plus x squared lemon. Right? It has some. Why does this make sense? Well, you think about convolution, right? Think about convolution. Convolution is sort of averaging, right? And when you're basically taking averages taking a weighted average of the C over 1. And so, it's not going to, it's basically going to give you C over 1. Anyway, if you want, I'll work out the details, but that's roughly, roughly how it works. Yeah, what?
The integral bounded by c
Yeah.
is because f is a one-degree decrease.
Exactly. Yeah. Right. Because it's this thing is integrable. Right? This thing is integrable. Right? And all you've done is shifted it over and over. Okay. So then we want to show, so the two estimates together, estimates A and B, give us the vanishing and infinity. Okay, so first, let's use B. So remember, we have a sort of particular kind of vanishing infinity, right? So as x plus y goes to infinity, we want to show that u of xy goes to 0. So basically we break it into cases. Case that your y is bigger than your x, then you use estimate b, right? Because we get the thing is controlled by c of y, right? And as y goes to infinity, this thing goes to 0. And then the other one, if x is greater than or equal to y, then you see that, well, we have that u of xy controlled by some constant 1 over 1 plus x squared plus y over x squared plus y squared. Right? But y is smaller than x, so we can replace this thing by y of x. Replace this thing by this, and we make it even bigger by throwing the y away, right? So you can just get rid of that, and it becomes bigger, right? And then as x goes to infinity, then this goes to 0. Okay, 15 minutes, good. It's enough time for me to do a lot more. Okay. Yeah, I hope we can get to it. William asked a question last time. Are we just lucky to get the approximation of identity? Maybe we have this differential equation, we have this PDE, the Fourier transform. Are we always going to have is it always going to be the case that we end up with that the solution is going to be a convolution with some kernel, and lo and behold, the kernel turns out to be an approximation of identity? Okay. The answer is, of course, no. But if you're curious about the phenomenon, look at this term, Green's functions. This is not exactly an answer, but it's along the lines.
Do you mean no, we're not lucky to know that doesn't always happen?
It doesn't always happen. So for certain differential equations, and I'm sort of stepping beyond my own knowledge, but for elliptic partial differential equations, then with certain conditions, then you'll have a Green's function, and you'll end up that the solution is something like a convolution with a kernel. It will end up that you have that the solution is the integral of the function against some function called the Green's function. And so this looks sort of like our convolution, right? Our convolutions are like this with k of x minus 1. Right? We have k of x minus 1. But instead of a convolution operator, you have some sort of kernel operator.
So it's true for all elliptic?
I don't know the details.
Okay.
I'm afraid. I should have studied more with the other big analysts. So there were two big name analysts at the University of Chicago. I shouldn't say that, there were others as well. But for me, these were the two guys who I considered to study. I ended up studying with Bob Beckman instead, and I didn't do so much with Carlos Kenny. Carlos Kenny is a big PDE guy, like one of the great humans of PDE. And Beckman is harmonic analyst, strong harmonic analyst. He is if you don't mind me telling some story, he is the younger brother of Charlie Beckman. No. He also an analyst. So Charlie Peppermint is sort of like known to be a genius, like genius among geniuses. He won the field medal, and he's one of the winners of the field medal. The story that I know is that he got his PhD when he was 19 at the University of Chicago, and immediately was made professor at the University of Chicago. And I think this is true because when I was there as a graduate student, you see the pictures of the professors on the wall, and they're like the assistant professors, blah blah blah. 1960 or whatever it was, the full professors, like all these old men, and then there's this kid. And so, apparently, he became full professor, very very early. And the story that I know is that 2 years later, he was. At age 21, he became full professor of Princeton. That's what he is now. So this is the big brother of my advisor, who being a late bloomer, got his PhD when he was 24. Anyways. So my experience as a graduate student was like this. I'd go in and Peppermint would say, so here's this problem I've been thinking about, and I don't know how to do this problem, but why do you think about it? And I'd be like, okay. It's like, I don't know how to do this problem. Why do you think about it for a while? So I go, I think about it for about a year, and I come back and sorry, Professor, I can't make any headway on this problem. He'd say, okay, I've been thinking about this other problem. It's again something that I can't understand, but I think there must be some connection between such and such Journet's lemma and this sort of thing. So okay, I'm going to think about it. And time passed, and I became old. Finally, I was thinking about. I was reading a paper, and I was trying to prove the result, sort of an interesting result. I was trying to prove it without using the proof that the authors had given. And I came up with a really cool fast proof. And then I realized I was completely wrong, that I had assumed that the operator that I was working with had some properties, and it didn't have those properties. But then I realized that actually this operator was actually suited to the problem and would give the results necessary. Okay, so I said, okay, well I'm going to define this new operator, and I've got this proof. I've got this proof, and further it gives us everything in a very easy manner. And that's how I got it out of graduate school. Yeah, but it took me a long time. Yeah. being a square advisor. Okay. So, mean value property. So, like I said, the next thing we're going to get is the uniqueness property. I guess I've wasted my time telling the story. To get uniqueness, we need something called the mean value property of harmonic functions. Okay, so the mean value property. This is just great. Just like the previous thing is also so great, right? You take your function, you want to find the harmonic function that converges to the boundary. Well, you can model with the Poisson kernel and get this thing that's harmonic, and it convolves. It's great. Okay, there's something I could like. So, what is the mean value property? Let omega be an open set, and let U be in C2 of omega. If U is harmonic in omega, then given any closed disk BR in omega, excuse me, closed disk, one has for all R between 0 and capital R, that U of xy is equal to the integral of U of x plus R cosine theta y plus r sine theta dk, divided by 1 over 2 pi. So this is great, right? It says that the you have some omega, and you have some ball, some disk that lies inside of omega, right? Use your ball, and if you take the center and you integrate, you take the average of the function over any circle, then that average is the value of the center. The average of the function on any circle within this ball is the value of the function of the center. So any circle you take here, they all have the same, the average value is the same, namely the value of the function of the center. Okay. So maybe we'll prove it next time. Let's use it right now to get the theorem. No, I'm sorry. We don't have time to. So I'm going to do the proof of the mean value theorem. The next time we'll do the proof of the theorem. Okay. So it is a proof, and it's a pretty slick one. If we let U of r theta be U of x plus r cosine theta, y plus r sine theta, and then you take the fact that this is take the fact that little u is harmonic. Okay. If you express this, use the polar form of Poisson. Okay, express it in polar form, and then so the statement, this expressed in polar form, is basically equivalent to this statement, that U of partial of big U with respect to theta squared plus r partial of r du dr. That thing is equal to 0. Okay, so this is it looks a little bit, I don't know if it looks intimidating or not, but saying you integrate it, right? You take the whole thing, you integrate it. You integrate it, right? You integrate both sides, divide by 2 pi. Okay. And then let f of r denote the integral of u over the circle. Okay. Just for notation. And then the above turns into the above rewritten becomes r partial with respect to r df dr equals 1 over 2 pi integral 0 to pi negative p squared r squared. Right? So you see what we're doing, right? You just all we're doing is we move this thing to the left hand side, we integrate it, and then we introduce this notation. Okay. Nothing has happened. Okay. We move this thing to the left hand side. It's on the right hand side with it, but no, that's not going to confuse you. Right. We move this thing to the left hand side. We integrate. We average it, and then we introduce notation, and this is what it looks like. So nothing. I'm not even cheating you this time. I'm not cheating you at all this time. I think. Okay. So, okay. So then you notice that, well, look, big U is periodic. So the right hand side is 0. So this is 0. Right? Because we're a periodic function. You're integrating some periodic function over the full period. So you can okay. So what does that say? Like R d dr R df dr is 0. So that tells you that R df dr is 0. Right. We can assume that R is not 0. At the center, we're done. We know what happens at the center. Right? So just assume that R is not 0. Well, we see that I'm sorry, is constant. Right, so this thing is constant, right? This thing is non-zero. Right? So this is constant, right? Right? And then letting R go to 0, we see that the constant must be 0. The constant must be 0, and that means that the FDR must be 0. In other words, F is constant. But, right, F is constant, and then you say, well, look, F at 0 is just U of xy. Okay. F at 0 is U of xy. Right? And so we see that the constant is U of x1. Right? And so that tells you that F is equal to U of xy. Right? In other words, In other words, the average over every circle is U of xy, which is what you want. As a form, say 1 over 2 pi, 0 to 2 pi, x plus opposite theta, y plus sin theta, d theta is equal to U of x1 for all 1. Right, between 0 and 2. So this is a pretty cute proof of a maximal, I'm sorry, the mean value function. Any questions? Am I going too fast? Am I going too fast? Close your eyes for a second. Hold the finger if I'm going too fast. Hold the finger if I'm going too slow. Everything's all right? Good. Okay, so next time we'll see how the mean value property gives us the uniqueness of the solution. And this is related to something called the maximum principle, which you may have seen in complex analysis.